So our next speaker is another repeat offender, Pim van Pelt of IPNG Networks. He's best known for running Success in the past, bringing IPv6 to everyone. In this talk, I believe Pim is going to make good his promise from a few years back on bringing us a VPP machine pushing over a terabit. So please join me in welcoming Pim to the stage.
All right. Hey, guys. I got directed to be standing in the light. Hi, folks. My name is Pim. I am from the Netherlands. I sound American, but I'm not. I make this joke every time. I moved to Switzerland a while ago. In 2022, I was at DENOG16 in Hamburg, and I made a certain claim about an open source data plane. I have to say, this is not the latest slide deck. We talked about it a little bit before, so maybe the numbers are a little bit different, but bear with me as I go through. The load tests that we did on this tool were just yesterday, just in time compiled. Okay, so IPNG Networks, tiny ISP. You thought WOPCOM was in a weird place. Like, we're definitely in a weird place in Brüttizellen in Switzerland. Like, I don't even know if Freddy knows where that is. Okay, so we have 14 as well of these open source routers across Europe. So Frankfurt, Amsterdam, and the north of France, and Paris, and Geneva, and Zurich. So it's a 10 gig ring, essentially. We like peering, so we have a bunch of adjacencies. Also a vanity 4-digit AS number that I got from 6Access. Vector packet processing now is an open source data plane. It is super fast, runs in user space, takes away the network cards from the kernel, and just runs a user space process using DPDK, RDMA, VirtIO, a whole bunch of these libraries to do super, super fast forwarding. 100 million packets per second is definitely easy, not hard, easy with this thing. And it runs on any commodity, 86 or AMD or even ARM CPUs. Completely open source, no blobs attached. So I first started working on this in 2021. You can check out a talk, an in-depth talk about VPP at Volsdem, or 2 years ago in Hamburg, where I made this claim. I contributed to the Linux control plane, which puts these interfaces back from the data plane to the Linux kernel so you can run higher level control plane stuff like BGP and OSPF and ISAS, VRP, that type of stuff, just as you would on a normal Linux PC, except the data plane forwarding stays with DPDK and VirtIO super, super fast. This talk is actually a twofer. Number one, how I got rid of most IP addresses in the IPNG AS8298 backbone, and two, how I did a terabit plus and 1 billion packets per second using a normal PC, although it was not quite exactly normal. Okay, so VPP CTL is a tool that you get from the VPP Debian packages, and you can call this LCP create from 100 gigabit Ethernet 400 and give it a host interface called ICE0. So that thing comes up in the Linux kernel, and you can manipulate it just like you would any other Ethernet interface. You can give it an IP address and maybe create a subinterface on this VLAN tagged with Q101, give it a different MTU, some IP addresses, some defaults, and ping DENOG.de. So what happens here is the packet goes from the Linux kernel through this TUN tap into the data plane, and then it gets forwarded off into the internet. And when it comes back and is destined for an IP address on the control plane, we forward it into the TUN tap so the Linux kernel sees it again. So all traffic that goes through the machine you don't see when you were to TCP dump one of these interfaces, much like you might have seen before on a Juniper, say. The control plane is Linux, the data plane is VPP. Okay, who knows Babel? I didn't know it. Okay, cool. There are like 7 people or so that said, yes, I know what Babel is. Babel is an IGP, not too dissimilar from things like OSPF or ISIS. So you just use it to connect things together. Originally written for mesh wireless networks, but you can also use it on wired networks. And one of the things that I wanted to show is how might this work with IPv4 routes using IPv6 next hops. If you were here yesterday, there was also a talk about this stuff with cross-family AFI. So in this case, I'm using Bird. It has a very good implementation of Babel. And we can create adjacencies merely by starting to announce the Babel protocol on some interface here. And I've set one interface type on E star, so every interface that starts with E. And I've used the feature called extended next hop, which will use IPv6 next hops for IPv4 destinations, just like we saw yesterday. So quickly, an interface starts multicasting its ability to do Babel. If the other interface or the other machine is also Babel capable, an adjacency will form. Great. All right, we also learn these prefixes now from our neighbors. In this case, I want you to look at things that are light blue. I'm sorry if you're colorblind. So 10.1 here was learned. That's an IPv4/32. It's a loopback address on my neighbor. And if you look at the IPv4 routing table, it actually has this really weird 10.1 via INET6 on this link local address on interface E1. So this is one of those examples where we're using an IPv4 destination with an IPv6 next hop. And what the underlying infrastructure will do is, instead of ARPing, it will use neighbor discovery to find who am I sending this, on FE80 blah blah blah, my neighbor. That's kind of nice. So VPP already knows how to do cross-address family next hops. So I should probably add that to the GitHub repo that I saw in that talk yesterday. So we programmed the fib, and here you see as well an IPv4 destination with an IPv6 next hop. But it didn't work. That sucks. Everything I always try doesn't work initially. And this is because when you don't have an IPv4 address on the interface, VPP says, well, then I'm not going to accept IPv4 datagrams. You're not configuring me, so I'm just going to drop them for IP4 not enabled. So my first attempt to fix this is to force on IPv4 on interfaces every time that I have an interface plumbed to the Linux control plane. So the good news is this works. But the bad news is you don't see any intermediary hops responding. Gert, you had a question about this yesterday. Yeah? There is actually an RFC that says you should be responding from 192.0.0.2. as an IP address, which is for the sole purpose of responding ICMP4 on an IPv6 link if you don't have IPv4. Nobody implemented this, neither did we. Right, so that kind of sucks because PathMTU is now also broken. So that the traceroute doesn't work is not that important, but PathMTU is way more important. So my second one is to use unnumbered interfaces in VPP, where we'll borrow an IP address from a loopback interface and put it on the interface. And now I have the IP address on multiple interfaces, which does do forwarding, because now IP4 is obviously enabled on these interfaces, but also breaks in a different way, because VPP would not respond to ARP requests if they were not in my subnet. And because my subnet is /32, you will respond to no ARP requests. Damn. All right, so we went and fixed that by allowing these ARP requests on /32 host interfaces, because you would never be able to ARP otherwise. Fixed that in Gerrit. And then also inhibited the sync of these IP addresses from VPP to Linux. And the difference between the previous slide and this one is E0 and E1 now still only have a link local address. And all of the routes have a next hop that is link local. But the trace route works because when we need to source an ICMP error message, we'll just use the one that the data plane copied from loop 0. So this is really beautiful. I don't use Babel, though. I don't recommend necessarily using Babel. By the way, Babel is fantastic. No criticism to it at all. But it's not guaranteed to be loop-free always. And so if you're running 100 gig E between Frankfurt and Amsterdam, and then one of your links fails, you may briefly have a forwarding loop, which kind of does suck. In a wireless network, it's not as bad. But in a wired, fast network, it's definitely terrible. OK, so we use OSPF. OSPF has a really cool RFC. It's called 5838, and it's an absolute terrible, gross hack. And I face-planted when reading this. It says, I'll try to quote here, although IPv6 link local addresses could be used for next hops in IPv4, I'm like, cool, that's what I want. It's desirable to have IPv4 next hops. It's like, OK, fine. So what we'll do is we'll put the IPv4 address in the IPv6 field and just null out all the other bits at the top and call it a day. So that fundamentally breaks the ability to use IPv6 next hops, because we're using the field to sort of override an IPv4 address. So actually, really what they should have said in this RFC is you can never use IPv6 next hops with RFC 5838. But the community is really cool. And Santiago from the Bird team thought of a fix to this which would not even break any RFCs. And he added in Bird a function called update loopback adder, which scans all the interfaces locally on the machine and then prefers host addresses /32s and otherwise uses any OSPF stub addresses. And if those are also not available, any IP address we can find on the machine, and it sticks that in the field for this link state update for RFC 5838 to work. And now, all of a sudden, OSPF will work without an IP address where we just borrow it from the loopback. This is a match made in heaven. I had just fixed ARP resolution to work for VPP. In the Linux control plane, we can inhibit these unnumbered interfaces from showing up in the Linux side, and the Bird commit from Andre allows Bird to actually work with that. So now we can have exactly one IPv4 and IPv6 address on the chassis on loop 0, and as a bonus, all of our interfaces can share the BFD session now because we're only using link local for all OSPF links. So how that looks like now is in light blue, I'll turn off unnumbered sync, which by default would be on for backwards compatibility, and I'll do the same spiel here, but now I get E0 and E1 with a link local address instead of the IPv4 borrowed address from loop 0. I'll turn on BFD on all interfaces that start with an E, and I'll create an OSPFv3, which is the IPv6 OSPF, and I'll apply it to a channel called IPv4. So this is where we start using an IPv4 routing information using an IPv6 session on OSPFv3. Still with me? OK, so I'll also create like the normal v3 OSPF for OSPF6, which is boring and worked already. So what we now see is these OSPF neighbors established for OSPF4, but the router IP is actually link local. So we're using OSPFv3 now to signal IPv4 addresses. And I can learn all of my routes this way. In this case, I'm seeing a default and a 10/24 and this 10.4/31. All of them are learned via OSPF quite normally, and they're marked as on link, which allows my VPP router or Bird to know that these are actually /32s that we will find on an interface without an IPv4 address. The fib is programmed as per normal, and now the trace routes look like this, kind of nice. Each of these blue addresses here are ICMP errors that are sourced from a loopback address for IPv4 and IPv6, even though all the transit networks don't have any IP address at all. So how I rolled this out in my toy ISB is like this. In the beginning, each of the routers has a /32 and a /128 loop. This is quite normal, I would say. But they also had a whole stack of these /31 point-to-point networks between backbone links in the network. And for OSPFv3 and IPv6, these were /112s. By the way, in case you didn't know this, that would be weird to me, you never needed point-to-point IP addresses for IPv6. That would have always worked, so you may as well just delete them, and OSPFv3 and ICS will be fine. Anyway, I'll upgrade Bird with Andre's change and upgrade VPP with my change, which is a data plane restart. And at that point, I'll rename the thing called OSPF4, the old OSPF, and then I'll create a new empty OSPF4, which is going to be OSPFv3 with this RFC 5838. Then I'll move interfaces one by one, like from the old one to the new one. And then finally, OSPF4 old will be empty and I can delete it. And at the end of this, each of the routers in this picture will have exactly one IPv4 and IPv6 address. And this comes from my bash history. First thing I'll do with that sed command is add prepend 10 to the OSPF cost, which will raise the cost, right? If it was 10 before, it'll be 1,010 now, which will drain these links. And then I'll use that second sed to replace OSPF4 to OSPF4 old. I'll download a bunch of packages. Then I'll enter the data plane network namespace, whack VPP, restart it by installing all of these packages and Bird as well. Okay? How long do you think that took? Don't have to answer. It took 92 seconds. Like normally when you were to upgrade like a Silicon merchant vendor, this is minutes to hours if you have old machines like I do. And here this thing stays online and you can ping it, and at ping number 2 it was down, at ping 94 it was back up again. So that is restart the data plane, restart Bird, install all the packages obviously, turn up all the interfaces, grab adjacencies, download a full table, put it in the fib, And then 92 seconds later, we're up and running. However, I didn't move any interfaces yet, so they're now all in OSPF4 old. So the second step then is in my config file to move these things into an unnumbered situation so that I don't need to configure any IP addresses anymore on the interface. And that looks like this in that orange bubble there. So when I roll this out, I need to then move what used to be XE11 with an IP address, right, in the old OSPF into essentially this interface called DDLN1 in the new OSPF that is unnumbered. If I do that as well on the other side, well, then that adjacency comes up and everything just works per normal. That's kind of nice. So I can take all of these backbone links one by one with coffee in hand and then just move them from one OSPF to the other. And that actually works because OSPF will learn these routes twice, once in the old OSPF4 and once in the new OSPF4. And they will share these routes amongst themselves as E2. They will prefer E1. Don't want to waste too much time on this. No kittens were harmed. Traffic flowed, and I went from a couple of routers in Zurich to even more routers in Switzerland, and then the whole ring to do this in essentially one evening or one nightly maintenance, which got rid of 27/31s. By the way, AS8298 is an old AS, but it's a new LAR, so we only have a /24. So for us, this is actually pretty important. It's 50 IP addresses or so that we saved. Pretty cool. Now, who was at DENOG 14 2 years ago? All right. Who knows that I made a claim that I would do 1 billion packets per second? Because I did talk about it a lot on Twitter. OK, so I need to eventually take a picture. Because I've taken pictures of everyone so far, except for myself. OK. This is a computer, non-standard Dell. That forwards 1.4 terabits of traffic in one chassis. And I want to show you its performance stats. So first, the lab setup here. There's one machine in the middle that runs VPP, and it has 2 CPUs. And these are like non-standard CPUs, 8490H, which has 240 cores total, which is a lot. 160 lanes of PCI 5, which is like a huge amount. And then we stuck it full of ConnectX 6 and 7, as many as we could buy on eBay, essentially. By the way, NVIDIA, I'm looking at you right now. You really need to start sending me these cards, because it's hard to buy, even if you have money. So then on the left and the right, we have 2 other machines that are also quite large workstations with somewhat smaller CPUs, but still a lot of PCI bandwidth that we just stuck full of network cards to be able to generate all this load, right? So you not need only one, but you need 3 of these guys. Pretty terrible. And then at the top, Clyde is doing math, and he has this controller that starts all of these load tests on the left and right-hand machine, and then monitors with Prometheus the data plane performance. And without further ado, here's how you configure T-Rex. T-Rex is an open source load tester by Cisco. You can just download it and configure it with this YAML file that says, please use these PCI devices given these MAC addresses, and then start traffic, to these other destination MAC addresses, which would be the VPP machines, right? So I have 2 load testing methods. Like number one is to strip down VPP to use only one thread, which will make sure that I can calculate how much can one CPU do. I know that I have 240, but in its bare minimum, how much can one CPU do? So I'll start with 1,000 packets per second, and then maybe 1 million, and then 10, and then 100 million. And then eventually VPP will stop forwarding more traffic than an X amount, and that is the amount that one CPU thread would be able to do. And then I turn on VPP in its normal configuration, which is multi-threaded and can assign workers to receive queues in the hardware and then service all of these independently of one another with roughly a linear scaling. You'll see in a second that's not entirely true. And then I'll run in method 2 this load test that's just RFC 2544, ramp up from 0 to 100% of line, and see where you lose more than 1/10%, and call that the capacity of the machine. So method 1 looks like this. T-Rex has this really nice textual user interface that you can look at. What I'm doing here is a load test with 2x100 and 2x200 gig Ethernet. And I'm doing small packets. And I'm kind of saturating now the machine, the VPP machine, by sending it as much as it will handle, which is, by the way, pretty respectable. It's doing 254 million packets per second with essentially 4 CPU threads, right? Because it's using 4 ports. That's kind of nice. So I now know what is one CPU capable of doing. So here's a table that shows this. I can do a very cheap operation, like just a layer 2 cross-connect, one port in equals one port out. I can do IPv4, IPv6, or MPLS, or even other stuff like VXLAN encapsulation, SR, V6, and like all of these things, but I'll only talk about these 4. And if you only do 1,000 packets per second, at the top left you'll see here that every packet that goes through this Xeon took 1,143 CPU cycles. And you know that each CPU has like 2.2 gigahertz, and so you know what it would be able to do. But when you do more, like 1 million packets a second or 10 million packets per second, it gets greatly more efficient because this data plane is really good at amorting the same types of operations on multiple packets at the same time. So one core with layer 2 cross-connect can do roughly 33 million packets per second. And I'll remind you, this thing has 240 cores, so it's actually a beast. IPv4, IPv6, and MPLS all get a little bit slower because the operations are a little bit more complex. But still, it's respectable with MPLS being able to do roughly 19.5 million packets per second on one CPU. So at least I know. That's the baseline. And without further ado, now for reals, we turn on a bunch of these 100 gig ports on the load tester every 15 minutes and just go from 0 to 100% of line and then see what comes out the other side before there's too much packet loss. And at 11:15, we start this load test, and at 11:27, we hit 1 terabit. And at 12:39, the thing maxes out at 1,250 gigabits per second, which is about 102 million packets per second or so, using large packets, which are easier for VPP to switch because there's like less of them, right? So this thing easily does a terabit. And in fact, if we had more ConnectX 7 cards, it would probably do 2. So I'll come back in 2 years with that. But does it also do a lot of small packets? Like you'll note, most non-serious hardware salespeople will tell you, like, we load tested our thing, and our thing does up to 20 gigabits, which means with very big packets, right? Because as soon as you send a lot of small ones, it gets way harder for one of these to do. So we also went all the way back down to the smallest packet we're allowed to send, 64 bytes. And here, we start at 2235, every 15 minutes, turning on one port, going to as much as it can generate, and in this case, the load tester is a bottleneck. And it can do roughly maybe 60 or 70 million packets per second per 100 gig port. At 2250, the first port reaches 100 million packets per second. And then just after midnight, 736 million packets per second, which is 471 gigs of L1. So that's a half a terabit of L1 at 736. The reason why this is upsetting to me is because actually there's an updated slide that this should have been, and I'll tell you what the number is. You can review it later. We had a breakthrough over the weekend. Some friends of mine said, hey, we can tweak some flags on Mellanox. We did a load test yesterday during DENOG on the first day and achieved 923 million packets per second. So this is just short of 1 billion packets per second. It's a little bit of a shame that the slide here is off, but maybe in post I'll go edit that and republish another video. All right, here we go. 923 million, but 736 here is already a very respectable number for this little machine. And with that, I'm actually back on time again for you. And this is the lab, and it is currently generating about 2 kilowatts of power into packets, and then through DACs, and then back into heat as they get discarded by the T-Rex load testers again. It's a lot of fun to work on, and maybe like in a year or so, come back and actually do like 2 terabits for reals. And thanks again for those NICs, NVIDIA.
Thank you very much, Pim. Do we have any questions? One at the back there.
I love it. Make them run.
Hi, this is Tam from Hetzner. First of all, thanks for the great talk. Did you have any weird issues with reverse root lookup within VPP with different IP families, or did this work out of the box?
You said reversed route lookup, like RPF?
No, route reverse lookup, like you look up a route to a destination which needs another route.
No, indirect routes. No, that just works. Because it's the job of the control plane. Like in my case, Bird would say, hey, here's the thing, I'm going to resolve it to the ultimate, and then just program the fib directly. Although in VPP, indirect routes do work for things like MPLS label stacking. I didn't try it with IPv6, and maybe that's your question. Maybe I should, and report back if that broke or not.
All right, thank you.
Should work, famous last words.
Thanks. Do we have any more questions? I actually have one, if that's okay. Did you think about measuring the power consumption of this box while you were...
I did. So the middle machine here that is running 2 of these CPUs that are 420 watt TDP is running just over 1 kilowatt. That's not great. The CX7 as well is not cheap. It like really slurps a lot. And the ConnectX-6 is not terrible. Right, so we're thinking this entire machine on the main side, by the way, you can't see it, but it's actually a C19 plug. These things mean business. It's about 1 kilowatt per, fully loaded.
Does that change much with load?
Unfortunately, no, because I can explain. Like you assign workers, and DPDK will start a tight loop thread pulling the NIC. And if you said I wanted 200 workers, then it will start 200 CPU threads at 100% each. So that thing is going to blast 800 watts. Now, there is a thing you could do, which is changing the profile of interrupt-based DPDK to polling DPDK at a certain threshold. So you might say, look, I'm only doing 1 million packets per second. I have all these CPUs. So you don't turn them off. The workers stay running, but they go out of poll mode into interrupt mode until you hit a certain threshold, and then they go full blast again. So you could be a little bit more efficient. Yes.
Okay, thanks very much. A question online?
Where are the R86s?
Okay, that's someone who reads my blog. So the R86 would be roughly the size of one of the CPU coolers, yes. And they're really cool, small, embedded machines. They're like maybe 8 to a U. They're 40 millimeters high. They do about 25, 30 million packets a second each, and they're 18 watts. And by the way, this is actually a really interesting point. These are really big, beefy machines, but you can also scale down VPP all the way down to something super small that does 18 watts and costs $100. And VPP will still be very fast, comparatively. Thank you for the question.
Great. Well, thank you very much again, Pim. And we hope to see you and follow up on your promises.
2 years. Cheers.